So this is the 8th lecture, okay, for ring theory. So in the last lecture, what we have discussed? In the last lecture, we have discussed some prime and more on prime and maximal ideals, and more on, in fact, more on ideals, right? So from today, we are going to discuss ring homomorphisms and ring isomorphism and isomorphism theorems, right? So we're going to start ring homomorphism. My topic is ring homomorphism. Okay, so today I'll be little bit first. Okay, some of the things I will give just as an exercise. Okay, so be ready for that, because these things are whichever a little bit trivial, so I will give them as an exercise and the rest I will solve. Okay, so anyway, so today what is my topic? This is called ring homomorphism. So you know about, everyone at least know what is group homomorphism. The similar things works here. So what is that? A function f from R1 is a ring to R2 as a ring. So there is I have two ring, R1 and R2, is called a ring homomorphism. It should preserve the both the operation. There is two operation, right? It should preserve the operation, first operation as well as the second operation, right? So what is homomorphism? If you know, everybody should know what is the first operation. F of R1 plus R2, this is equals to f of R1 plus f of R2, and f of R1 R2, this is f of R1 f of R2, right? For every R1 comma R2 inside, R1 inside, no, R1 comma R2 inside R1 in the ring R1, right? So this is called ring homomorphism. If these two properties satisfy, then we say that this is a ring homomorphism, right? So whenever we have a homomorphism, so what we have initially, is, whenever we have a ring homomorphism, what we have? If you have a zero element of R1, the ring R1, so this f, if you operate f here, so it will give the zero element of R2, right? And also see here, zero element goes to zero element, or the additive identity 0, right? Additive identity of R1 is 0 and 0 goes to 0. And what you have is, you have, see here, f of 1, you can write 1 dot 1. This is actually f of 1 into f of 1, right? What is that? This is actually f of 1, right? This implies that f of 1 times common, like f of 1 minus 1, right? F of 1, yeah, you just take it to be here, and f of 1 minus 1, this is 0. So this is 0. This means that this is either 0 or a 0 divisor. So f of 0 and f of 1 is 0 or 1. See, f of 0 or if it is 0, then this will imply that f of 1 equals to 1, right? So 1 or a 0 divisor. Anyway, we don't need, but just an idea here. So okay, whenever you have a homomorphism, so zero element goes to additive identity, goes to the additive identity, add the unit element, or the 1. If you have this 1, so this 1 goes to either 0 or 1 or the 0 divisor. Okay, if your ring contains the unity, right? So whenever you have a homomorphism, so you can talk about the kernel and the range space. let me range of f. What is range of f? We are collecting all the fx such that x inside R1. This is range f. You have to verify the first. What is kernel? Kernel if all those x inside R1 such that f of x is 0. The additive identity is 0, right? So you know you can talk about then. So in the group theory, what you have is in the kernel is a normal subgroup, right? So here what you can say is kernel is a ideal in R1. So what you have to prove? I am giving you some homeworks here. These are some homework. So first question that to prove that range of f is a subring of R2. Okay, and the 2 you have to prove that this kernel of f is an ideal in R1. Very easy to check, just go through the definition. Okay, the third thing I am going to prove here. So these two are homework. So image of idempotent, in fact idempotent or nilpotent, whatever, idempotent or nilpotent means idempotent also the nilpotent, image of under homomorphism is idempotent or nilpotent. Image of an idempotent nilpotent under the is idempotent or nilpotent. So I'll prove for the idempotent. I'll give it as exercise for the nilpotent. So prove. How do you prove? This is very easy to prove. Suppose if R1 to R2 is a ring homo, right? What you have to prove? Image of an idempotent. That means you have a, suppose that you have an element, let R1 be an element of R1. So what you have is R1 square equals to R1 because of idempotent, right? Because of the idempotent, R1 square equals to what can you say about f of R1 square? You can say f of R1. So also you can say that from here this implies that f of R1 this is equals to f of R1. This means that f of R1 square this is equals to f of R1. Idempotent in range space or the codomain space. Okay, so this f of R1 square is equals to f of R1. This implies that idempotents. Similarly, you can talk about the nilpotents. Okay, so idempotents and nilpotents preserves the homomorphism. Sorry, homomorphism preserves the idempotency and the nilpotency. Okay. So okay, let me give some example here. I have defined. So if suppose f is a map, if it's a homomorphism or not, you have to check zx, that is sort of all polynomial in one variable x to z. And how to define for the map? F of this is evaluation map. F of any polynomial you can take px here, you just evaluate at p0, p0. So can you show this map f is a homomorphism? Can you show? Plus on to, can you show this map? Why this is onto? Because homomorphism check is just you have to check for the two property. Okay, let me check first, because this is the first example. I am not going to give you the exercise for the homomorphism. Let me verify. Okay, so suppose you have p and q, two polynomial in zx. What you have to verify for the plus, right? F of p plus q. You have to show this is f of p plus f of q. This is actually f of p plus q means f of, that means p plus q at 0. It's not it. This is actually p0 plus q0. What is that? This is actually f of p plus f of q. Am I clear? So first operation is preserving. What about the second f of pq? What is that? This is actually pq at 0, which is actually p at 0, q at 0. What is that? P at 0, q at 0 means f of p, f of q. So this is a homomorphism. F is a homomorphism. So homomorphism. What about the range? Why this is onto? What can you think about the range? Range of the function f. Range is actually all those p0 such that p and px inside zx. This is the, is not it? This is the range, right? So p0. So can you see this is entire z for any p0 here? So 0, you can evaluate it at 0, and you can make it the entire z. So this is going to be onto. This implies onto. So if it is onto and homomorphism, can you do you know the first isomorphism theorem for the group? Do you know the first isomorphism theorem for the group? The similar thing is will work here. So first isomorphism, what it says? Okay, so for first isomorphism theorem, what you need is, you need what is the kernel f. So what do you think about the kernel of the function f? Kernel is all those polynomials in the zx such that the map is from zx to z, right? F of p 0. It's not it. What does it mean? That all those polynomial p inside zx such that p0 is 0, right? If p0 is 0, so can't you see this is if p0 is 0, that means there is no constant time. Constant time is 0. p0 means the constant time. So can't you see this is the polynomial generated by the ideal generated by x. X will generate the entire polynomial, because there is no constant time, because p0 is 0, the constant time is 0. So what do you think now? What can you think about the first isomorphism theorem now? What do you think? So G mod kernel f, G means z of x, mod ideal generated by x is isomorphic to the image z, because of onto by first iso theorem. I will define here also first isomorphism theorem, and I will prove also, but do not worry about that. Okay, so that's all. Now I am going to give you some statements and a proof. One I will prove here, and another one I will give it as exercise, right? So what is the first statement I am going to write is, because this kind of proofs are very easy and trivial, I guess. So let me write one. So I will prove that, suppose you have a ring. So before that I have to write, let R be a ring. Let R be a ring and P be a ideal in R. So what you have to prove is, first you will prove that R mod P is integral domain if and only if P is a prime ideal, right? Prime ideal in R. How do you show? How do you show for that? Just a second. How do you show that R mod P? R mod P is an integral domain if and only if R mod P is an integral domain, or you can say R mod P is without zero divisor, because what is the definition of integral domain? Integral domain means it has no zero divisor. It has no zero divisor. So what do you think about the proof? Can you think of the proof now? Okay, suppose the first equality you can show. So suppose the proof I am going the forward part. How will you suppose R mod P is integral domain. Okay, R be a commutative ring with unity. You have to assume. Okay, I think I don't need the commutative ring with unity. So anyways, let's prove it. Let's see whether it has creates a problem or not for the commutativity and the unity. So anyways, so R mod P is an integral domain and AB inside P. Okay, you have to show either A is inside P or B is inside P. That's it, right? It's not it. I have to show to show that R mod P is an integral domain, and what you have is AB and AB inside P. You have to show P is a prime ideal. That means either A is inside P or B is inside P, right? So what you can do is, see, R mod P is an integral domain. That means it has no zero divisor. So what you can do is A plus P, B plus P. So if A plus B and B plus P, because A plus P and you have to show that it has no zero divisor, so it P. Okay, so this implies that AB plus P, this is equals to P. Since P is a member of, okay, so I think there is no need for that. So A plus P, B plus P, what is that? This is actually AB plus B. This is the coset operation, right? Because AG is a member of P, that means this is P. Can't you see? This is so A plus, this implies that A plus, this is a zero element, right? So A plus B, B plus P, this is P. Can't you see? So this implies that, see, it has no zero divisor. This is an integral domain. It will definitely imply that either this is 0 or this is 0. There is two elements and it is still giving us 0. This is a non-zero element. If it is a non-zero element and it is a non-zero element, it's still giving you 0. So it cannot happen, because this is you are in an integral domain. You are in an integral domain. So for the it has no zero divisor, right? It cannot be both of them are non-zero. It cannot happen. So either this implies that either A plus B equals to P, or A plus P equals to A. Here is P, right? P. Just a second. A plus P and B plus P. P is an ideal. Okay, P stands for prime. So anyways, so this implies that, okay, this implies that A plus P, B plus P is equals to AB plus P, right? AB plus P means P, because P is a member of P, AB is a member of P, right? So this implies there is two element and it will giving you 0, and you are in a integral domain, right? So it has no zero divisor. This will definitely imply that A plus P is P or B plus P is P. Okay, that means either a plus p is 0 or b, that means a plus p is 0 or b plus p is 0. Okay, 0 means p. Okay, this implies that two cosets are same if one only a inside p or p inside p. So this is the definition of, we have assumed that a b inside p and we are getting either a inside p or b inside p, right? So we are getting that p is a prime ideal. So this implies that, this is essentially implies that p is right. Now what can you think about the reverse part? Suppose you have, what you have, suppose you have the ideal p is a prime ideal and you have to show R mod p is an integral domain. How do you show it for the integral domain? For the integral domain part, how do you show for the integral domain? Suppose you have the p is a prime ideal, right? So you have to show this is an integral domain. That means it has no zero. You have to show this has no zero divisor. Suppose, so let's prove the reverse part. P is prime ideal. P is prime ideal, and to show R mod p is an integral domain. That means you have to show it has no zero divisor. It has no zero divisor. No zero divisor, right? So what do you think about the a plus p, b plus p? See, we have assumed that this is a prime ideal. Okay, what is the definition of prime ideal? A b inside p. This implies either a inside p or b inside p, right? So what is a plus p and b plus p? What is a plus p and b plus p? This is actually, okay, see, this is actually you have to show this has no zero divisor, right? It has it has no zero divisor. That means one of them has to be, you have to show it has no zero divisor. This is actually AB plus P. It's not it. So you have to show that this is a you have to show that this is an integral domain, right? Integral domain, that means you have to show this has no zero divisor. So a plus p and b plus p, what you can okay, what is the best thing you can do is a plus p, b plus p, and c. Okay, you have to assume that a so R mod p is an integral. You have to show that R mod p is an integral domain. So a plus p, let me just think little bit how should I proceed. So anyways, so we have to show R mod p has no zero divisor. Has no zero divisor means no zero divisor means that means one of them has to be equals to 0, right? It if you can show one of them has to be equals to 0, so no, so then we will be done. What do you think about the a plus p? So okay, a and b are the members of the whatever the R is an R, yeah, R for the integral domain R. So do I need a commutativity here? Commutative ring with unity or something? So it has, you have to show it has no zero divisor. You have to show, so there cannot have any 0 divisor. That means one of them has to be equals to 0. If you can show, then we will be done. And okay, what you have, if you are in P is a prime ideal, so AB inside P implies that A inside P or B inside P, right? You have this. So what do you think about A plus P, B plus P? Okay, so either A inside P or B inside P. Okay. So AB inside P. Okay, AB inside P. You have AB inside P, and this implies that either A inside P or B inside P. Suppose A inside P. What does it mean? This implies that. So not this implies. This equals C. If A is in P, so this will be 0 plus P, because A will be dominated here. A will be, because A is inside P. This is into B plus P. B plus P will be as usual. So what is that? This is actually 0 plus P. This is actually 0. Are you getting my point? Actually I am getting my point right now. So there is no need any commutativity here. So A plus P and B plus P, what do you think? So if suppose, so we have assumed that this is our prime ideal, right? So prime ideal means if A B inside P, this should definitely imply that either A is inside P or B is inside P, right? It's not it. Are you getting my point? Suppose without loss of generality, I am assuming that A inside P. If A is at P, then A plus P will be, A will be already here. So A plus P does not make any sense here. So A plus P means 0 plus P, because A is already here. So 0 plus P. So P can be written as 0 plus P, and B plus P as usual. So this is P. Okay, this is P. So this implies that A plus P and B plus P 0. A plus P and B plus P. So A plus P, B plus P is equals to P, which is the 0 element, right, of R mod P, which is the 0 element. This implies that AB plus P is equals to P. This implies that two cosets are same if only AB inside P. This implies that A inside P or B inside P, because of the primality. Are you getting my point? Similarly, if without loss of generality, if you take B to be in P, then this will be 0 and this will be still this, it will be C, it will be P, right? So that's the idea actually. Okay, that's the actual idea, or you can proceed for in that format. So what is A plus P, B plus P? This will be AB plus P and AB inside P. So AB inside PP, it will be definitely be 0. So anyways, you can definitely proceed like that. Okay, so this completes the proof. So R mod P is an integral domain if and only if P is prime. This kind of statements are very useful. Okay, otherwise you by seeing an structure of a quotient structure, you cannot predict whether an ideal is going to be prime or something maximal. You cannot. So for that reason, you have to remind this kind of statements, right? So first one is this statement, and what about the second statement? What is the second statement? Second statement needs the what is called is commutative and the unity. So what you have is the second statement says that R is a CRU commutative ring with unity. R mod M is a field if and only if M is maximal. In R. Are you getting my point? So this I am giving you as a homework, because this is also easy, nothing. So this two statement you have to keep in your mind, right? So first statement is this: R mod P is an integral domain if and only P is a prime. Okay. And the second statement, R is a CRO, R mod M is a field if and only if M is a maximal ideal in R. Okay. So that's the okay. Just keep in your mind these two and just note it. Okay. Now I am going to start. Okay. Also, do you need one more homework here? So question 3. Should I give? So just try it. If C01 is a, that means this is a structure actually. C01 set of all continuous function from C01 to R. Okay. Such that f of half is 0 is maximal in C01. Check this two as an homework. Okay, I'm giving you as an homework. So now I'm going to start some new topic. No, not new. This is called the first isomorphism theorem. Morphism theorem, the first isomorphism theorem. Okay, this is, although this is not very useful here, but little bit useful. The main thing we'll need here is of third isomorphism theorem for the ideal generated by two elements. So anyways, I'm going to, what is first isomorphism theorem? You know, everyone should know what is that. Similar group theory thing is there. Okay, so if phi, suppose R to S, I'm not going to write properly, but you have to assume that R is a ring, S is also a ring, and there is a map from R to S. Be a ring homomorphism, ring homo, then first of all that kernel phi is an ideal of R, and range phi is a subring of S, and the theorem says that R mod kernel phi is isomorphic to image of phi. This is called the first isomorphism theorem. This is called the first isomorphism theorem. Are you getting my point? What is first isomorphism theorem? So you can definitely, I guess you can prove it definitely, because the proof is not so hard. The same proof, the same structure, the same construction for the mapping is as usual in group theory, whatever you have learned in the first isomorphism theorem. Okay, let me just give you the hint here, because these are very easy, very easy to prove, right? So what you can do, you can define a map psi, right? First of all, you can define a map psi R mod kernel phi to, from where you can define the map as. So R mod kernel phi to image of. How do you define the map? How this map actually looks like? Some R kernel phi, because these are some cosets, kernel phi. Okay, this goes to phi of R. Are you getting my point? Can you see that this map is a well defined and a homomorphism and a 1 and onto? That means this is going to be an isomorphism. Are you getting my point? Actually, oh my god, R mod kernel not is R mod kernel phi. You can write it as R plus kernel phi, because in group theory what do they have to coset? So R plus kernel phi is actually phi of, this is actually phi of R. Phi of R, whatever the map we have defined as a phi here, phi is a homomorphism is defined, right? So can you say this map is an, this phi, this is well defined, also homomorphism plus bijection. This will prove that this R mod kernel phi is isomorphic to image of phi. This is called the first isomorphism theorem. Okay, proof is very easy, you don't need to bother too much here. This is called the first isomorphism theorem, right? So first isomorphism theorem has been over. So now I am going to write what is a projection map. Handwriting is going to be, what is a projection map? You know, natural projection. Let's try to make the handwriting little bit good. Natural the speed is violating, my speed is violating. If I go for the handwriting, but then my speed is little bit slow. So anyways, so what is that? The projection map, we know whatever this is, the projection map is. So anyways, what is natural projection? Suppose if I is an ideal in R is a ring. I'll always assume R is a ring. And what is, suppose pi is a map from R to R mod I. How do we define for the map? Pi of R, this is actually R plus I, and this is an onto ring homo, because checking for the ring homomorphism onto is easy, because you can take any element here, you can of course guess the image. So what about the, whether this is a homomorphism or not? So pi of R1 plus R2 is actually R1 plus R2 plus I. What does it mean? R1 plus I plus R2 plus I. This essentially implies that pi of R1 plus pi of R2. Similarly for pi of R1 R2, I am not going to write everything, whatever it is. So this is called a natural projection. Now I am going to write the second isomorphism theorem. What is called, you know, in the second isomorphism for theorem for the group, the similar thing is working here. So that's why I am going little bit first here, because you have already studied in the group theory course, right? So anyways, what is second isomorphism theorem? Let's suppose that A be a subring A be a subring of R and B is an ideal of R. So you have a one subring and this is one ideal, right? Then how can I define A plus B? A plus B is all those A plus B as usual, such that A is inside A, B is inside B. So this is a subring of R. First you have to show, and then A intersection B is an ideal of A. So in the group theory, what we have was the A plus B is a subgroup of the group G, and A intersection B is a normal subgroup, the group of the normal subgroup of A, because A was a subgroup and B was initially our the normal subgroup, and A intersection B is a normal subgroup of A. So whatever here, this is actually it's converts into the ideal. That's it. There is no other thing here. It's happened which is new. Okay. So and what else it says? It says that A plus B quotiented by B, because B is an ideal, so we can quotient this. This is isomorphic to A mod A intersection B, because A intersection B is an ideal of A. That's it. So this is called the second isomorphism theorem. So do I need to prove this theorem? So I think the proof is similar kind of proof is here. So similar thing, just you have to show for the second property. Was first property how to show, and just you have to show for the let's prove it, no problem. So let's prove it. So any statement without proof is not valid actually. So let's define a map from A to A plus B mod B quotiented by B. How do you define for the map? F of A is goes to A plus B. Is this map is well defined map? You can check, at least you can check. Homomorphism well defined, this is well defined clearly, and homomorphism and onto. F is plus onto. If it is onto, so you can define the you can talk about, if you have the kernel, you can talk about the first isomorphism theorem, because you have already proved the first isomorphism theorem. So before that you need the kernel. What is kernel of F? This is actually all those A inside the domain A such that F of A is zero element. What is the zero element here? This is B. Is not it? Are you getting my point? So what A such that what is F of A? It means A plus B is equals to B, right? What is that? F of A inside A such that two cosets of same if one only be A inside B. So A inside A also A inside B. This implies that this is A intersection B. So you know, so kernel is an ideal. I have just given kernel is a normal subgroup, right? You know, so kernel is also an ideal. I have in this lecture I have given you to the exercise that kernel is an ideal, right? Kernel is an ideal of the domain ring, right? Of the domain ring. So this is going to be kernel F. So this is an ideal of the domain ring A. So the first, this proves the theorem, proves that A intersection B is an ideal of A. Okay, because kernel is A intersection B, and this is an ideal of A. That's it, right? Are you getting my point? So what else is? Now you use the first isomorphism theorem, that will prove, that will serve the whole argument. So how will prove? So what is our, so you can prove this, since this is a homomorphism plus onto, so we can talk about the first isomorphism theorem. A quotiented by A intersection B is isomorphic to, since this is an onto, so it will be isomorphic to A plus B by B. A plus B quotiented by B. So this proves the theorem of second isomorphism theorem. Second iso theorem. Okay, are you getting my point? So this kind of things are a little bit easy. So I'll give one more theorem here. This is called the third isomorphism theorem. The third isomorphism theorem. So similar for this I am again saying that this is most important for the ideal generated by two elements. This take it to be seriously, right? This the third isomorphism, because in the group theory course there was no uses of the third isomorphism. That's the rare uses, but in the ring theory course you will use oftenly. Anyways, so what is this? What is that? Let I comma j are two ideals of R. Are you getting my point? What I am, and I is contained in J. You have two ideal I and J, and I is contained in J. Then what the theorem says that, so J you can see, if you have this, so J I is smaller, I is contained, so J mod I, you can define J mod I is an ideal of R mod I. Are you getting my point? So let I and J be two ideal and I is contained in J. See, I is smaller than J, right? I is contained in J. So I mod J is an ideal of R mod I. R mod I. So, and what it else is said, and R mod I quotiented by you have to use in R mod I quotiented by J mod I. Quotiented by J mod I is isomorphic to R mod J. This is called the third isomorphism theorem. See, R mod I, see J mod I is an ideal of R mod I, so you can definitely define R mod I quotiented by J mod I, and this is isomorphic to R mod J. Am I clear with you? I think I should clear. Okay, am I clear with you? So that's the theorem here. How do you show? How do you prove here? So I will prove this theorem. Do not worry, I will prove this theorem. So the statement is clear or not? I and J be two ideal and I is contained in J, and that means one ideal is contained in another. Then you can define J mod I, because J is bigger and I is smaller, and I is also an ideal of J. So it is an ideal of R mod I. If it is an ideal of R mod I, you can define R mod I by J mod I. R mod I quotiented by J mod I. So R mod I quotiented by J mod I is isomorphic to R mod J. This is called the third isomorphism theorem. So I will prove it. So for the proof, how do you prove that? Suppose you have a function f from R mod I to R mod J. You have defined a function R mod I to R mod J. Let's look how we will define this function f of R plus I is equals to R plus J. This is a very natural map, right? You can basically verify this is onto also. Clearly this is onto, because you take any R plus J, you just give a pre-image here. So onto plus homomorphism. Because this is very easy. I'm not going to, and I don't want to waste time here by proving this kind of things. So anyways, R plus J, R plus I, R plus J. Okay, this is an onto ring homomorphism. So what can you think about the kernel of this map? How do you so all those R plus I inside R mod I such that f of R plus I is going to be zero element of R mod J. What is there? This is J. What is that? This is actually all those R plus I inside R mod I such that R plus J is equals to J. Two cosets are same if and only if. So what is that? R plus I inside R mod I such that two cosets are same if and only if R inside J. R inside J. Are you getting my point? If R inside J and R plus I inside R mod I. So does this, can you see here that this is actually nothing but J mod I? How do you show? Because see here, R is an idea, should be inside R R is an element of R from here, and R is an element of J. So this means that, so you want all those R plus I such that R is an element of J. Also R is an element of, if all R is an element of J, right? R is an element of J and R is an element of R. Also here R is an element of R, also R is an element of J. So R intersection J is J na, because J is an ideal of R. So this is, so this is why the J mod I, this is quotiented by J mod I, because I is as usual, you just want to, because R is an I and R is in J, the J is smaller, so R should be also in R, or R should be also in J, so R mod J is J. So this implies that this is J mod I. This is the kernel of the function, kernel of the homomorphism. So if you have the kernel, you can what you have the map R mod I. So R mod I by J mod I is isomorphic to R mod J, because this map is onto. So proof is very easy. Has anything difficult here in the proof? So G mod kernel, no, sorry, R mod the kernel. What is my R? So again you are using, I'm repeatedly using the first isomorphism theorem. R mod I, see here, R mod I quotiented by kernel. Kernel means J mod I is isomorphic to the image. Image is the entire space, because the function is onto. So this proves the theorem that this R mod I is isomorphic to R mod J. Okay, J mod I is an ideal of, because kernel is an ideal of R mod I. This proves from here for the kernel part. Okay, this proves the third isomorphism. Okay, so I think I am done with today, because I'm not going to start anything, because I will in the next lecture I will solve some questions, and I can give some question here, you can try, but I will not solve them today because I don't have any time today. So anyways, so what is the some homeworks? So ideal generated by 2, what you can do is 2 1 plus x square is not maximal in ZX. Prove or disprove? Question number 1, prove or disprove, right? So question number 2, what you can show is, so yeah, for this question you can solve, and rest I will solve in the next lecture, and then we will define the Boolean ring. After that I will define for the Chinese remainder theorem. After that the Euclidean domains. So anyways, so this is the homework, right? So these two, ideal generated by 2 comma 1 plus x square is not maximal in ZX. You just prove or disprove this. If you can prove, then prove, and if you cannot prove, then give me a counter example. So, or you can show that this is not maximal ideal in ZX. Okay, so prove it, right? So this is for today. I am going to end this lecture. Goodbye everyone, we'll meet in the next lecture. Thanks for watching.